Welcome to the lecture series on process integration. This is module 1, lecture 1. The topic of the lecture is process integration, methods and application. In this lecture, I will introduce the concept of process integration, and while doing so, I shall derive it from the nature. Let us see a natural phenomena which takes place in nature, and the example is that how the birds fly. Many birds fly in flocks as shown in the picture, but why do birds flock? There are a number of social factors for this, which include reproduction, protection from predators, communication and navigation, etc. But let us look at only at the aerodynamic factors for the time being. One theory is that there is an aerodynamic advantage to flying behind and to the side of another bird to take advantages of its wingtip vortices. Birds fly in a V shape to help conserve their energy during migration. With the exception of the individual leading the group, each bird trailing behind the other benefit from a reduction in wind resistance. This formation reduces the drag force that each bird experiences compared to if it were flying alone. So, it clearly tells that if birds are flying in flocks, they conserve energy, or I can say that the per unit consumption of energy, that means consumption of energy per bird in a flock is less, and this is for flying. The same phenomena we can see in the nature when the fish swim. So, let us take the case of the fish. Fish swim in schools, and why this happens? They do this mainly because of two simple facts of nature. The one is big fish eat little fish, and two, there is safety in numbers. The size of the shape and often the flashing of light reflected off thousands of the fish can confuse the predator, but being in a school also means that predators cannot generally eat the lot, and so significant numbers survive. But these are not the technical reasons for it. So, let us see the technical reason why the fish swim in schools. There are other reasons for fish to swim in schools. One reason is that they swim and their trails sweep from side to side. They set up tiny whirlpools or vortices in the water, which effectively reduces the friction for each of a fish neighbor. Less friction means less effort, and energy is reduced in swimming. That means the techniques which these animals or the birds and fishes apply in nature, there is an inherent concept of integration in them. So, where then integrate their flying styles, integrate their swimming styles, they consume less energy. This is also Other examples, through other examples we can show this also, like joint family. If we take a joint family, then we find that expenditure per person decreases in a joint family, stress level per person also decreases in a joint family, and logistics requirement per person also decreases. So, joint family, which is an integration of individuals, due to this integration we see that these are the benefits, that is expenditure decreases, stress level decreases, and logistic requirements also decreases. A latest concept which is aquaponics, there we integrate fish farming with vegetable growing. The fishes help the vegetable to grow, and vegetable also helps fishes in terms of their food. So, in the nature there is a lot of concepts which are available, and so that integration helps each other. So, a conclusion we can draw from the nature that integration of any process leads to many useful outcomes like saving energy, minimizing logistics, and better economy. Now, the question is that do we have a technology which mimics this concept? Because this we have learned that together we all win, and this is a new concept and which is available in the nature. Can we translate this concept to our industry? So, the question is, do we have a technology which mimics this concept? The answer is yes. It is process integration, or in other word we can say process pinch technology, which mimics this. So, the integration is the key to better design and operation. Let us slowly, this concept will unfold, and we will see that how we bring out this betterment in design and operation through process integration. Let us see an application of process integration in the industries. In the older days, when gold is to be extracted by amalgamation process using mercury, we see that the stirring and other things are integrated with water wheel. So, by integrating, a lot of work can be done simultaneously. This is being used in the old industries for extraction of gold. Now, if you see the energy scenario of the industry, that what are the energy available to the industry, how much energy available to the industry, and how much useful energy out of the energy available is used in the industry. So, red part of this graph shows that the every industry is losing a large amount of energy when utilizing the energy available to it. Now, the question is, can we decrease this energy loss from the industry through design or through process integration? Now, from this example which has been there in the screen, let us see that how a better design can be given through process integration. We see the left hand side picture, there we see that the whole process, which as a reactor, a say flash drum, and there are few heaters. If we take this traditional design, the minimum heating requirement was 1722 units. It has 3 heat exchangers 2 heaters and 1 cooler, and minimum cooling requirement was 654 units and number of units were 6. So, this was a traditional design. When on this design, the concept of process integration was applied, then the design was simplified, and now it requires only 1068 units of minimum heating. A lot of heating requirement has been decreased, almost about 700, some 40 odd units of heating has been decreased, and cooling has been made equal to 0. That means, in the improved design we do not need cooling utility, that is cold water. That means, a complete area of the industry which handles the coolant or cooling requirement or cooling utility is now off. That means, we do not need a cooling tower even. So, this is a big achievement and big reduction in the cost. Further, the number of units required is 4. That means, we are able to save the utilities, we are able to save the number of units which are required for the operation of this process. In this, we have not compromised anywhere. That means, the output is the same, the steam stream temperatures or the exit temperatures of the streams are the same, and reaction inlet temperatures and outlet temperature of the reactor is the same. Everything remains same, but the process is oriented in such a way, designed in such a way using the integration principles, that it gives you a lot of saving. Now, the question is, can this design procedure, the process integration, which is based on the thermodynamics, can help us to save capital cost and energy. For this, we go to the figure, the left hand side figure. Here there are 3 hot streams which has inlet temperature of 300 degree centigrades and outlet temperature of 200 degree centigrades, and there are 3 cold streams which has inlet temperature as 50 degree centigrade and outlet temperature as 150 degree centigrade. Now, we know from the design that Q is equal to U A delta T ln. That means, if I can increase the delta T ln, if U remains constant, then A decreases. So, if I heat the cold streams using heat which is at the highest temperature, that means more than 150 degree centigrade, and if the cooling water is at the lowest temperature, maybe 25 degree centigrade, 30 degree centigrade, then the delta T available for this design is very high, and if the delta T ln is high, then area will be less. So, this is a concept. In this design, we will see that this concept does not work perfectly. So, I expect that this design will give me the minimum capital cost as my area will be minimum. This type of design is appropriate when energy is cheap and the capital is expensive, because in this design there is no concept of heat recovery, and I am using only the utility to meet my targets. Now, let us take the second case, which is in the right hand side. Here every cold stream is exchanging heat with every hot stream, and there is no heater present and there is no cooler present, because cooler and heaters are shown in dotted lines, and the stream and cooling water is also shown in dotted lines. So, these are absent in this design. Now, here I am using the full concept of process heat recovery. This design is appropriate when energy is expensive. Heat recovery as much as possible is done in this design and no utility is used. So, these are two extreme ends of design. In one end, I am utilizing the heat recovery completely, and in the other I am not utilizing it. So, let us compare these two things, because I expect that in the case B, my fixed cost will be very high, as I am saving energy through process heat recovery. Now, the question is this thought process is correct? So, if we quantitatively analyze this two concepts, then for A, where I am using the utilities completely to satisfy the cold streams as well as hot streams, the area requirement is 204 units. Now, in the case B, when I am using the heat exchange completely, I am not using any utility cost, I am using 3 heat exchangers to exchange the heat. My area requirement is only 133. Now, this is a result which is completely against our earlier thought process. The area has decreased, that means the fixed cost has decreased in the case B, as well as I am saving a lot of utility, because I am going for complete exchange of heat in the network. So, in both case I am gaining. In capital case, capital cost as well as the running cost. Now, the question is why this has happened. This may be against the general thinking, general rules. Now, let us examine this. These examples indicate that there are two basic thermodynamic effects influencing capital cost. One is the effect of driving force, that is delta T, which we have seen in the equation Q is equal to U A delta T ln. But the second effect, the other is the effect of heat load. This we have not considered in our design. It is evident that as we go to tighter designs, that means reducing the driving force, we need less utility and the overall heat load decreases. And this fact was not considered in the earlier analysis. Capital cost then increases with reduced driving force, that we know from Q is equal to U A delta T, but decreases with reduced load, we rarely consider this point. And what has happened in this design? In the design without process heat recovery handles twice as much heat as is necessary, and hence in part A of the design, the total area requirement is 204, because it is handling twice the amount of heat almost as in the case of B. In the design without process heat recovery, it handles twice as much heat as is necessary. As a result, capital costs are increased even though the driving force are large. Now, what we have observed, that when we are increasing the driving force of a heat exchanger network, the capital cost decreases, and this is given by this line. So, when we are increasing the driving force, the capital cost decreases. However, when we are increasing the driving force, the heat load increases. This is a new fact which has come out, and hence we saw that even increasing the driving force is not decreasing the area of heat exchanger, that is fixed cost, as much as we were expecting, because it increases the heat load. So, we cannot apply exactly the formula Q is equal to U A delta T, because when we are changing the delta T or increasing the delta T, Q is also increasing. Q is equal to U A delta T is applied in those areas when changing delta T, Q is not changing. Now, if you see the scenarios of successive plants with time, then we find that if this is the minimum energy requirement for a industry, we find that the old processes, the design was somewhere here. So, there was a large gap between the minimum energy consumption and the energy the industry used to consume. With the time, this gap is decreasing. This is with conventional design. So, if I am going for design through traditional methods or conventional method, this is the graph I am following, where this gap, the energy consumption gap and minimum energy gap is decreasing. However, if we use a design which is based on process integration or thermal integration, we will formulate a design which is somewhere here, which is very close to the minimum. So, if we are improving our design of thermal integration using process integration principles, we will be able to give better designs which will be near to the minimum energy consumption. Now, if you see the process design of a chemical industry, then a chemical industry is converting raw material to the products using a chemical change, and this chemical change is brought about using a reactor. So, the central portion of a chemical industry is a reactor. So, the design of a process starts with the reactor in the core of this onion diagram, which brings chemical changes in the field. Then when I am going for a reactor, if I am converting A to B, the B will not only be formed, with this C and D will also be formed, which are byproducts. So, we need a separation process for this. So, my second layer is, once feed, products and recycled concentrations and flow rates are known, then we have to design the separators, the second layer, because without separating the byproducts from the product, I cannot sell the product in the market. So, my second layer is a separation layer. Then I have a third layer, which is called heat exchanger layer, because for the separation we need energy. Like for example, in a distillation column, two liquid components are separated with heat energy. So, based on the requirement of heat for the core and the second layer, the heat exchange network, the third layer, can be designed. and the fourth layer, which is the utility layer. So, the remaining heating and cooling duties are handled by the utility system, the fourth layer. So, a chemical industry can be visualized as a onion having many layers, and that is why this diagram is called a onion diagram. Now, the process integration, the concept of process integration can be used in all the 4 layers. We can use it for reactors, we can use it for separators. In the separator it becomes mass exchange, mass integration, for it here it becomes heat integrations. And so, on the whole diagram, the onion diagram, we can use our process integration principle. Now, let us use this onion diagram and connect to a process flow diagram. This is a process flow diagram. Here the feed is entering, this is a reactor. So, in the reactor I am getting output which contains feed, unreacted feed, then products and byproducts. These are at higher temperature, this exchanges heat with a incoming feed, and then the products which are the product plus byproducts, it goes to this product which is the feed plus product plus byproduct goes to a separation system. At the bottom of the separation system I get product and byproduct, and the unreacted feed goes here, which exchanges it with a cold utility, comes here, and a part goes from here and it exchanges heat here, and then it is again fed to the reactor. So, and a bottom product from this say distillation column goes here, exchanges heat, that means it is heated up, and then it is goes as feed to this distillation column. Then a part of this byproduct goes to a separator which may be a flash drum, where I am getting product and byproduct. So, these are two mass exchange equipment which are doing mass exchange. So, they fall to the layer of separation. This is reactor, it falls to the reactor layer which is in the core, and these are heat exchanges, they fall to the Hens layer, heat exchanger network layer, and then these are heater and coolers where they also fall to the Hen layer, but here I have shown that the cold utility and hot utility which is being used here fall to the utility layer. So, here we have taken a small PFD and we have shown that how the part of this PFDs are related to the onion diagram. Now, let us see what process integration is. Let us see some definitions. Process integration, a part of process intensification, is a fairly new term that emerged in 80s and has been extensively used in the 90s to describe certain systems oriented activities related primary to cover almost complete process design. It is a holistic approach to process design, retrofitting and operation of industrial plants, with applications focused on resource conservation, pollution prevention and energy management. It enables the process engineer to see the big picture first and the details later. In the process integration, we draw the big picture first. We believe that if the big picture is correct, then we should go for the details later on. That means, we can analyze the details later on. the first aim is to create the big picture first, and this big picture is created using process of integration. Process integration is concerned to the advanced management of material, energy and information flows in a production plant and the surrounding community based on the multi criteria optimization of the processing systems. Now, if you see the definition of the PI, there are many definitions which were given to the PI by different people. One definition is it is a systematic and general methods for designing integrated production systems ranging from individual processes to total sites, with special emphasis on the efficient use of energy and reducing environmental effects. Another definition is process integration is seen as a group of methods to optimize the use of energy, but with concerns for environmental aspects. Rositer and Kumana in 1995 gave this definition, state that process integration methods include focus on ensuring that existing process technologies are selected and interconnected in the most effective ways rather than attempting to invent new type of equipment or unit operation. This definition slightly touches the potential synergic effects which will be achieved by integration. According to the Halwagi in 1997, integration emphasizes the unity of the process. According to him, process integration is a holistic approach to process design, retrofitting and operation which emphasizes the unity of the process. Other definitions in 1997, the IEA, which is International Energy Agency, broadened their definition of process integration to mean the application of methodologies developed for system oriented and integrated approaches to industrial process plants designed for both new and retrofit applications. Latter, Natural Resources Canada in 2003 defined process integration as all improvements made to process systems, their constituent unit operations and their interaction to maximize the effective use of energy, water and raw material. According to the Friedler, in 2010, process integration has been defined as is a family of methodologies for combining several processes to reduce consumption of resources or harmful emission to the environment. So, what we saw in these definitions, the concept of integration is that the concept of integration of equipment. Why? To decrease the energy required for the process and to stop or to decrease the harmful emissions. Now, if you see the evolution of process design from history to the future. So, in the first generation what we used to do, the process design used to be start with experiments in chemist laboratory and then tested in pilot plants before plant construction. Then came the second generation. Here we use the concept of unit operation, and unit operation acted as building blocks for the engineers in the design process. Now, in the third generation of process design, the concept of integration came into picture. So, the integration between units came into picture, for example, heat recovery between related process streams to save energy. And in the fourth generation, we considered more than one process phenomena taking place in a equipment, that is reaction, heat transfer, mass transfer etcetera, to take place within the same piece of equipment, and doing this a significant savings can be observed. It is a part of process intensification, which is a fourth generation process design concept. Now, let us see the current status of process integration. Process integration is a strongly growing field of process engineering. It is now a standard curriculum for process engineers in both chemical and mechanical engineering at most of the universities around the world, either as a separate topic or as a part of a process design or synthesis course. Research at UMIST in this area for last 27 years or so has been supported by a large number of industrial companies through a consortium that was established in 1984. As a part of the International Energy Agency IEA project on process integration, 35 other universities around the world are involved in this research field. So, this shows you the current status of the process integration, how much work is being carried out in different universities of this world. Now, let us see what are the classification of process integration methods. This hierarchical analysis, it can be divided into 4 quadrants. The first quadrant is interactive and qualitative, the second is qualitative and automatic, third quadrant is automatic and quantitative, and fourth is quantitative and interactive. Now, if you see the first quadrant, in the first quadrant we use historic rules, and this gives insight about the design and economy. Now, if you see the second quadrant, here we use the knowledge based systems. These are the rule based approaches with the ability to handle qualitative or fuzzy knowledge. In the third quadrant, we use the optimization methods. So, these are the methods or which can be used for process integration purposes. So, in the optimization methods, we use deterministic, mathematical programming and non-deterministic methods. And the fourth one, which is quantitative and interactive, here we use the thermodynamic methods, and the pinch analysis has become very famous and based on thermodynamic method is used with focus on thermodynamics. So, how the process integration is tackled is shown by these 4 quadrants, and each quadrant can handle the process integration processes. But the pinch technology area, which falls in the 4th quadrant, is the scope of this lecture series. Now, the techniques for process integration, let us see what are the different techniques which are available for process integration. The pinch technology approach, which we have seen in the 4th quadrant, can solve it. Process graph theory can also be used for process integration purposes. Genetic algorithm approach, which is basically optimization technique, can be used for process integration. State space approach can also be used for process integration, and MILP and MINLP approaches can also be used for process integration. So, the process integration has a profound effect on the chemical process industries in the form of pinch technology and heat exchanger network optimization, which obviously falls, we have seen in the 4th quadrant. Now, as this method is becoming very popular, it can be used for several applications. If you see the applications, we see here the energy integration, we can use it for heat exchanger network design, for cogeneration and total site targeting, for distillation column targeting we can use, for batch process targeting and optimization we can use, and we can use for low temperature processes. So, when we talk about energy integration, these 5 topics come to our mind. Then it can also be used for hydrogen management in refineries. Basically, if you see the PI applications, we go for heat integration and mass integration, and the hydrogen management in refineries fall under mass integration. So, if you see the mass integration also, here we can go for water and wastewater management and recovery of valuable materials we can go. Then for pollution prevention we can use, basically it is a mass integration and a energy integration process. We can go for carbon constrained energy sector planning, we can go for water and wastewater management, we can go for recovery of valuable materials, we can go for emission targeting and this method or in this application area. Then we can go for debottlenecking of critical areas in process industries using pinch technology. We can even use it for financial management, we can use it for supply chain management, and we can use for co-production systems. So, we see here that the pinch technology or the process integration has got a broad area of application. Now, to show you that how this has become so broad, the application has become so broad. Let us see the analogies for application of unified targeting algorithm UTA to diverse integration problems. Senoy in 2011 suggested a single algorithm to establish minimum resource targets for diverse process integration problems, including those of heat and mass exchange, water, hydrogen, carbon emission and material reuse networks, and proposed unified targeting algorithm ETA. Now, if we see this, only we see a part of it, that is heat and mass integration. So, the variables for heat exchange network, the level or quality is temperature, that is the driving force is temperature. For mass exchange network, the driving force is composition or mass ratio. If I say the flow of quantity, for heat exchange network it is heat capacity flow rate, and for mass exchange network it is mass flow rate kg per second. Load or quantity, if you see, that is heat load for heat exchange network, and for mass exchange network this is mass load. High level resource or utilities, here for heat exchange network hot utilities, that is steam, hot water or Dowtherm, and in the mass exchange network this is process MSS, and for low level resources in utilities, the cold utility is used for heat exchanger network, and for mass exchanger network this is external MSS. Level of shifting which is used for heat exchanger network is delta T minimum by 2, and there in the mass exchange network we use the delta Y minimum by 2 or epsilon by 2. And level sort orders, when we are sorting the temperature levels or the concentration levels, that is from in the decreasing order, also mass exchange network it is decreasing order. So, Senoy has given a unified algorithm for the utilization of PI in different areas. Now, let us come to the pinch technology, which is a technology which is being used for process integration. So, it is a methodology for minimizing energy consumption of processes by computing thermodynamically feasible energy targets or minimum energy consumption and achieving them by optimizing heat recovery systems, energy supply methods and process operating conditions. It is also known as process integration, heat integration energy integration or pinch technology. AspenTech's Nick Halale has reported that pinch analysis for energy has an enormous amount of application, with thousands of projects having been carried out all over the world. Companies such as Shell, Exxon, BP, Amoco, etc., Mitsubishi have reported fuel savings up to 25% and similar emission reduction worth millions of dollars per year. So, it shows the effectiveness of the pinch analysis and how this analysis is saving the energy and reducing pollution in worldwide. Among PI methodologies, pinch analysis is currently the most widely used, because it provides a lot of insight to you when designing. This is due to the simplicity of its underlying concepts and especially to the spectacular results it has obtained in numerous projects worldwide. It is a systematic methodology based on thermodynamic principles to achieve utility savings by better process heat integration, maximizing heat recovery and reducing the external utility loads, that is cooling, water or heating steam. Pinch technology is a well proven method in industries such as chemical, petrochemical, oil refining, paper and pulp, food and drinks, steel and metallurgy, etc., leading to an energy saving of 10 to 35%, water saving of the tune of 25 to 40% and hydrogen saving up to 20%. Now, here we see some graphical representations of the savings which it can done. Here we see the oil refining sectors, the saving is from 10 to 40%, and here we are talking about potential energy saving due to heat integration. And in the iron and steel industries, it is 11 to 50%. For chemical industries, about 15 to 40% saving can be achieved. Paper and pulp, 10 to 35% of energy saving can be achieved. Food and drinks industries, 7 to 45%, and textile about 3 to 25% energy savings can be done using the pinch technology. Now, if you go for the water savings, then the same technology, what is called water pinch, if applied on the industries, oil refinery, it can save 10 to 40% of the water. For bulk chemicals, 25 to 35%, for specialty chemicals, 20 to 60% water saving, pulp and paper, 10 to 30% water saving, food and drinks, 30 to 40% water saving, and most other like textile, polymer, etc., 20 to 40% water saving. So, this is a huge amount of saving which can be done using process integration and when applied to our industry. Now, the problems of process industry related to energy is that most of the industries in the third world are the technology is borrowed, often obsolete technology. Energy consumption per unit production much higher than in western industries, no concept of process integration. So, the energy management through process integration has become a reality. The problems of Indian industry can be solved by using techniques that minimize energy consumption with minimum investment using this process integration technique. So, process integration is one such techniques or one such tool which can do a lot of good to our industry. Now, generally problems which are addressed are of two types. One is called creating new designs, and this is related to the design of a new plant which is in design stage, and the other is called retrofitting or revamping of existing design. If you have a existing design, we can still apply the process integration or pinch technology to cause saving. This is related to the retrofitting of an already existing heat exchanger network in a plant to improve its exchange efficiency. Now, how it works? So, we first take the problem where we want to apply pinch technology or the process integration, then we collect the data, then we transpose to stream problems, and then we draw composite curves, then we define our targets, which can be energy targets, area targets, it can be number of units target, number of sales target, it can be cost targets, etcetera, etcetera. Then we design to meet those targets. So, design with pinch rules, and then we transpose back to a new PFD. So, we start with a PFD of the existing plant, and then we give a new PFD based on process integration. And if this new PFD is implemented, then a lot of saving can be done. So, once the PFD is with us, then we go for simulation and feasibility checks, and once we are satisfied with the simulation feasibility check, then this final design is accepted and implemented in the industry, and these are the references. Thank you.